Let's solve the hardest AP Calculus question of 2025. So there are actually two AP Calculus courses, Calculus AB and Calculus BC, and we're going to be solving the hardest question from both of them. So what do we mean by hardest? The College Board actually releases the average score students got for each question. In both courses, for the question with the lowest score, students got approximately 35%. And in the hardest part of each question, students got 6 and 7%. Bro. The hardest part in both courses are actually very similar, and we're going to go through a method that just makes it super simple to solve. The crazy thing is, both of the hardest questions were in the calculator parts of the exam, so students didn't struggle as much with actually doing integration or differentiation. It was more so like not understanding what the question really wants, and students also just didn't like justify their answer properly. By the way, the hardest question of Calculus AB was also on the BC exam. BC students didn't find it as hard, but it's still a useful exercise. Alright, so first we're going to solve the question from Calculus AB, and if you just want to skip ahead to the question from Calculus BC, you can use the timestamp here. So yeah, this was the hardest question of the year for Calculus AB. The average score for AB students was around 36%. So yeah, let's break it down. Okay, so let's read the question. An invasive species of plant appears in a fruit grove at time t equals 0 and begins to spread. The function c of t equals 7.6 arctan 0.2t models the number of acres in the fruit grove affected by the species t weeks after the species appears. And then they give us the formula for the derivative of c, which is actually very useful. Now let's read part A. So it says find the average number of acres affected by the invasive species from time t equals 0 to time t equals 4. Show the setup for your calculation. To find the average of like a bunch of numbers, it's pretty simple. You just add the numbers up and divide by the amount of numbers. But to find the average of a function, it's different. So let's say we want to find the average value of a function across a certain interval. This is the general formula. In our case, the starting point of our interval is 0. So a equals 0, b equals 4, and our function is just c of t. You can score 2 points in this question, and this is all you need to score 1 point. This part of the question is in the calculator portion of the exam, so we don't even have to show our work. We can just put this in a Desmos and get our answer. Okay, first thing we're going to do is define the function c of t. This is going to save you so much time in parts B, C, and D. And it's also just going to reduce the number of typing errors you could possibly make. To do integration in Desmos, you just type int, and then next we just fill in our limits, and then type c of t over here. And then at the end, we just type in dt, and we get the answer 2.778. So yeah, this question wasn't too bad. We just have to know the average formula for functions. And remember to always round to 3 decimal places. And it's good to write a conclusion sentence like this. Okay, moving on to part B. It says, find the time t when the instantaneous rate of change of c equals the average rate of change of c over the time interval 0 to 4. Show the setup for your calculation. Okay, so the first thing we need to find is the instantaneous rate of change of c. And what do derivatives do? Derivatives give you the instantaneous rate of change of a function. So all we need is this c dash t over here. And lucky for us, the question actually gives us the formula for c dash t over here, which we'll use later on. Next, we need to find the average rate of change of a function, and there are basically 2 ways to understand or derive this formula. So yeah, we want to find the average rate of change over the interval a to b. So what we're going to do is take the total amount the function changed and divide it by the total amount the input changed. If we think of it in terms of graphs, so we let y equals f of x, this becomes the total amount y changed divided by the total amount x changed. And remember, we're just working over the interval from a to b here, and so this becomes f of b minus f of a divided by b minus a. There is also a sneaky way on how to get this formula. Remember how in part A we used an integral to find the average value of a function? And we just talked about how the derivative gives you the instantaneous rate of change of a function. How do we get the average rate of change? We just use the average value integral formula on the derivative. And now we have formulas for both the average and the instantaneous rate of change. And so for the average rate of change, let's just plug it into Desmos. Since we already defined the function in part A, the calculation becomes really simple. We just type the slash to get the fraction, and then we just literally type in our formula. And we're left with this 1.282 figure over here. For the calculation, I just recommend leaving as many decimal points as possible, just makes us be more accurate. And for the instantaneous rate of change, remember the question already gave us the formula for c dash t. And so all we got to do is find the value t such that the instantaneous rate of change equals this 1.282 figure. So we multiply both sides of the equation by the denominator here, and we also divide both sides by this 1.282. And then we subtract 25 from both sides, and then take the square root. And that's all we need. Remember to round to 3 decimal points. Assume that the invasive species continues to spread according to the given model for all times t greater than 0. Write a limit expression that describes the end behavior of the rate of change in the numbers of acres affected. Evaluate the limit. The question is asking us to write a limit expression for the rate of change. That means we're going to be working with derivatives because that's just what derivatives are. Derivatives give you the rate of change of a function. Lucky for us, the question already gave us the derivative, which is c dash t over here. The question is asking us to write a limit expression that describes the end behavior of the rate of change. This whole question is about modeling how an infection spreads over time, and so the end behavior just means as time goes on and on forever, or in other words, as t goes to infinity. And so this becomes the limit that we're dealing with. To begin, let's just focus on the denominator. Now, as t gets bigger, 25 plus t squared will be even bigger than t, and so as t goes to infinity, the whole denominator will be infinity. And now we have a constant divided by infinity. Let's think about it for a bit. Like 38 divided by 1000 is 0.038, and 38 divided by 1 billion, for example, is 0.000, it goes on, 0.38. And so, as this whole denominator gets bigger, this limit gets closer and closer to 0. And so the limit equals 0. The other method is we just put the function into Desmos and see the graph as x gets bigger. In this case, we can see it just goes to 0. In general, though, you got to be a bit careful because you never know, the graph might change as x gets bigger. So yeah, that's all for part C. Hope y'all are able to follow my explanations well. And yeah, let's move on to part D. All right, so now moving on to part D. This is the part where only 7% of students got it completely correct. And the thing they messed up with was not actually their final answer, but their justification. So part D basically defines this function a of t, and it's asking us to find the maximum value of this function from t equals 4 to t equals 36. In general, to find the maximum point of a function, the first step is to find the values where the derivative equals 0. And so let's calculate the derivative of this a of t function here. Obviously with respect to t. In a of t, we are subtracting two functions, and so we can differentiate both parts independently, or one by one. So obviously the derivative of the function c of t is just c dash t, which the question gave us the formula for. Now let's focus on differentiating this integral thing here. To do this, we're going to be using the fundamental theorem of calculus, which is something your teacher should have taught you in class. But basically it says that differentiation and integration just cancel each other out. However, there is one thing we got to be really careful about, and it's that notice that we're differentiating with respect to the variable t. And if we want to cancel out the integral with the derivative, we have to make sure that t is in the bound of integration here. Notice that we are integrating with respect to x here and not t, which is exactly what we want so that t can be in the limits or the bounds of integration, which is what we need to properly apply the fundamental theorem of calculus and have the derivative and integral cancel themselves out. And we're left with this minus 0.1 ln t here, not x. And remember, the question gave us the formula for c dash t already, so we just plug it in and we're left with this equation here. We want to find the maximum point of a, so let's set a dash t equal to 0, and then move this 0.1 ln t to the other side. And we're left with this equation here. Thing is, right, this equation is pretty much impossible to solve algebraically, but what we can do is plug it into Desmos like so. Desmos will only graph something if you use x and y as the variables, so we just put in x instead of t into our equations here. And we can see the graphs intersect when t equals 11.4417. Now that we have this value of t here, we need to justify that it will lead to a maximum point and not something like a minimum. This is actually the part most people messed up on. In fact, only 7% of students actually got this part right. One mistake people made is that they used the second derivative test, which is basically you calculate the second derivative, and if it's less than 0, then you know it's a maximum point. But the second derivative test only works in a small interval around the point. To see why it doesn't work in general, let's look at an example. Let's look at this point L here. The second derivative test will show that this is a maximum point, and around a small interval like this, it is true. But if we expand our interval, we can clearly see there are points bigger than L. So yeah, the second derivative test will help you find a local maximum or minimum point, but to find a general or absolute maximum point, it won't work. Now that we know the second derivative test won't work, let me show you a method on how to justify if something's a maximum or minimum point when we're working over a closed interval. There are other methods you can use, it's just that they take a bit more work and they are a lot more prone to error. This method is by far the simplest and I highly recommend that you use it. So there's this theorem called the extreme value theorem. And basically, it says that the maximum or minimum value of a function over a closed interval is either at a point where the derivative equals 0 or it is at one of the endpoints. And so to find the maximum point, all we got to do is calculate the value of the function at the endpoints and this t-value that we have here and see which is biggest. The question is asking us to find the maximum point when t is between 4 and 36. If we define the function a of t in Desmos, you can easily plug in all three values, and you'll notice that the maximum point is not at the endpoints, it's actually when t equals 11.442. And so yeah, that's our answer. Be careful, some people might put this 7.316 as the answer, but this is the maximum value of the function, but the question is actually asking us for the value t where the function attains the maximum. So yeah, make sure to put t equals 11.442 as your answer. And so yeah, that's it. You can see this question actually wasn't too hard. It's just that people really messed up their explanation. And it's all because the justification method they used is either just wrong or like just harder, so they make more mistakes. This type of question gets asked really often, to find the maximum or minimum point of a function over a closed interval. And students really often just get their justification wrong and lose marks. And that's why I tell my students, when you see a question like this, use this method. So yeah, that's part D done, and question 1. That was the hardest part and the hardest question in all of AP Calculus AB. Hope I was able to explain it well. And I do math tutoring, by the way, so if you're interested, links are in the description. Okay, let's look at the hardest question of the year for Calculus BC. It does involve polar coordinates, so for AB students, it's not part of your exam, but for BC students, it's super important. This question is mainly differentiation and integration involving polar coordinates. So yeah, you gotta be really good with your polar coordinate formulas. Let's get into the question. Curve C is defined by the polar equation r theta equals 2 sine squared theta for theta between 0 and pi. Curve C and the semicircle r equals half are shown below. So part A, it says find the rate of change of r with respect to theta at the point on curve C where theta equals 1.3. Okay, so we need to find the rate of change. And in a calculus course, if you hear rate of change, 9 times out of 10, they want you to calculate a derivative. In this case, we need to find the rate of change of r with respect to theta. So we need to find dr by d theta at the point where theta equals 1.3. This question is in the calculator portion of the exam, so let's just head into Desmos. Okay, our question is about polar functions, and we can actually change Desmos to be in polar coordinates too by clicking this little wrench icon here, and then in the grid section, you click on the icon where it's like circular. Okay, so the question gives us the function r in terms of theta here, and you'll save so much time if you just define this function in Desmos first. It just makes calculations way simpler. The question is asking us to find the derivative at the point where theta equals 1.3. And so all we have to do is just type this r dash and parentheses 1.3 over here, and we get our answer. Just make sure to round to 3 decimal points. And yeah, this wasn't too hard of a part. Okay, so question 2, it says find the area under the curve C, but outside the polar equation r equals 1/2, which is the semicircle thing here. Whenever you're working with area under a curve or areas and functions together, the first thing that should pop up in your head is, oh, we're going to be doing integration. And yeah, so this is the region we're trying to find the area for. It is inside C, but outside the semicircle. We got to be careful though. We can't just find the entire area under C and then subtract it by the entire area under the semicircle, because there are parts of the semicircle that are outside C. So we have to be a bit careful about what limits we choose for our integration so that we calculate exactly the area of only the shaded region. I want you to focus on the intersection points between the curve and the semicircle. Let's visualize what would happen if we use these intersection points as our bounds for integration. But remember, in polar coordinates, if you want to find the area of something, you have to use this formula. I'll show the exact working for the integrals later, but this is the region we get if we find the area inside C with these bounds. And now let's subtract the area we get under the semicircle with these bounds. And look, we're left with exactly the shaded region we wanted from before. Now let's actually do the math. The first thing we need to do is find the intersection points. The semicircle and the curve will only intersect when their equations are equal to each other. And so yeah, let's set 2 sine squared theta equal to 1/2. Okay, so let's divide both sides by 2 and take a square root on both sides. And remember, square roots give you both a positive and a negative solution, and so we're left with sine theta equals 0.5 and sine theta equals minus 0.5. So now we just apply arc sine on both 0.5 and negative 0.5, and we're just left with theta equals these two values. Now we have our limits for the integral, and so this is what we're left with. And since we are in the calculator portion of the exam, you can literally just put this into Desmos and you get your answer. Okay, so part C, this is the part where only 6% of Calculus BC students got completely correct. Let's read the question. It can be shown that dx by d theta equals this equation here. For theta from 0 to pi upon 2, find the value of theta that corresponds to the point on curve C that is farthest from the y-axis. Okay, so first things first, the question says we're working with theta from 0 to pi upon 2. In polar coordinates, pi upon 2 is just 90 degrees. So the question is basically asking us to work in the first quadrant here. So they want us to find the point that is farthest from the y-axis. Okay, let's visualize it for a second. We are working in the first quadrant here. And so to get the point farther away from the y-axis, we have to move the point more and more towards the right. And how do we move a point more towards the right? We have to make the x-coordinate bigger. So yeah, to find the point that is farthest from the y-axis, we have to find the point with the maximum x value. Okay, as soon as you see maximize or minimize a point, you know you have to calculate a derivative. So this part is actually really similar to the hardest part in question 1, which we solved earlier, where a lot of students messed up the final answer, but almost everybody messed up the justification. We are also trying to find the maximum point over a closed interval here. And so first we find the point where the derivative equals 0. But the big mistake people make is using the wrong method to justify that it is actually a maximum point. A lot of students use the second derivative test, which is just wrong, unfortunately. And we explained why in our solution to question 1. Or they use the method that is more complicated or error prone than the one I'm about to show you. The crazy thing is only 6% of students actually got full points for their justification. And with our method, it's actually pretty simple. So yeah, let's continue. We are working in a closed interval here. For us, it is theta from 0 to pi upon 2. In general, for closed intervals, the maximum or minimum point will occur either when the derivative equals 0 or at one of the endpoints. This fact is called the extreme value theorem. And so all we need to do to properly justify if something is a maximum point is to calculate the values of the function at these points and see which one is biggest. Okay, so from our graph, we can see that the point farthest from the y-axis is clearly not at one of the endpoints, but the examiners require formal justification, even though the endpoints are literally just on the y-axis. The crazy thing is only 6% of students actually got full points for their justification, and with our method, it's actually pretty simple. So yeah, let's continue. Even though polar functions are normally defined by their distance from the origin, there are also formulas to find just the x-coordinate too. And lucky for us, the question actually gave us the derivative for that formula, dx by d theta. So we set this equal to 0, and we need to find the values of theta for which this equation holds true. Okay, so for the first step, notice that we can actually factor out 2 sine theta here. Okay, so now notice that we are actually just multiplying two things here. First one is 2 sine theta, and the second one is what's in the parentheses here. If we multiply two things, the only way the answer can be 0 is if one of those things is also 0. Okay, so first let's focus on 2 sine theta. In our interval, theta is from 0 to pi upon 2, and in that interval, 2 sine theta is only 0 when theta is also equal to 0. Theta equaling 0 is already one of our endpoints, so we were going to consider that point anyway. So for now, we can just divide both sides of the equation by 2 sine theta and focus just on what's in the parentheses. So what we do here is we add sine squared theta to both sides, and then we divide both sides by cos squared theta, and we're left with tan squared theta equals 2. After a bit more work, we're left with theta equals 0.955. Now we just need to justify that this value of theta will actually lead to a maximum point. In other justification methods, you might have to calculate a second derivative or consider when the derivative is positive and negative. But for us, it's just really simple. All we have to do is take our value of theta and the values of the endpoints and plug them into our formula for the x coordinate here. And then just see which one is biggest. Make sure to use the formula for x and not r because because we're just trying to maximize x in this question. And we can clearly see that at the endpoints of the interval, the x value equals 0, which checks out with our graph. And the biggest one is clearly when theta equals 0.955. Make sure to put theta equals 0.955 here as your answer and not like x equals 0.7698 or 770, because the question is specifically asking for the value of theta that corresponds to the point that is farthest from the y-axis. So yeah, this was the hardest part of the hardest question in all of AP Calculus for 2025. And it was actually a pretty hard question. The key takeaways is to be really good with your polar coordinates and make sure to use our method for justifying if something is a maximum or minimum point. So many students mess up here, but with our method, it's really simple. And if you have watched this video, you can score points where most students miss out. Okay, so part D, it says a particle is traveling along the curve C so that d theta by dt is equal to 15 for all times t. Find the rate at which the particle's distance from the origin changes with respect to time when the particle is at the point where theta equals 1.3. So yeah, the question is asking us to find the rate at which the distance from the origin changes. So rate of change. And when you think of rate of change, what do you think of? Derivatives. So yeah, we need to calculate a derivative here. So yeah, it's asking for the rate at which the distance from the origin changes. And in polar coordinates, the distance from the origin is just the function r, which we have defined already. So we're differentiating the function r with respect to the time t. So we need to find dr by dt at the point where theta equals 1.3. But the function r is not defined with respect to t. So how do we differentiate it? Well, what we do have is that d theta by dt equals 15. And also in part A, we calculated dr by d theta at the point where theta equals 1.3. And now I hope your teacher has taught you, but derivatives, while not like this dr by d theta thing here, they're not technically fractions, but they behave almost exactly like one. And so if we multiply dr by d theta by dt, you notice that the d thetas actually cancel each other out, and we're left with dr by dt. And so all we need to do is plug in our values, and we get dr by dt equals 15.465. Make sure to round to 3 decimal places, and it's always good to write a sentence like this. And that's all for the hardest Calculus BC question of 2025. Hope I was able to explain things clearly. If y'all enjoyed, leave a like and subscribe. I also offer math tutoring, by the way. So if you're interested, check out the links below. And thank y'all for watching.